Hey everybody, we are back for section 9.2, Introduction to Sampling Distributions. So first definition here. The sampling distribution of the sample mean is the probability distribution of all values of the sample mean when all possible samples of size n are taken from a population. That is a loaded definition. There's a lot of things going on. And I'm going to break that down for you in just a minute. Before I do that, I just want to talk about this second point here. There's sampling distributions for all statistics, for all sorts of statistics. Sample variance, sample standard deviation, so on and so forth. But in this course, we will mainly be focusing on the sampling distribution of the sample mean. So that's what I gave you the definition for. That's what we're going to be focusing on. Okay, now let's break down this definition. And the best way to do that is, I'm going to give you two examples, but let's start with this first example, which is actually in the textbook. If you want to take a look at that, I'm going to pull it open right here. It has to do with valve measurements. So, in this example, they have 6 valves, labeled A through F, and they measure the diameter of each valve, as you can see in the second column here. Well, then they found the mean, 0.1483. Then they also found the standard deviation. All right, so if we go down to this second table, valve sample measurements, n equals 2. This n represents sample size, right? So we've been talking about random samples, and there needs to be a size, right, with every sample. And for this specific example, our sample size is 2, which is a little small, but the whole point right now is to kind of show you guys how this works. Most of the time, we're going to be working with bigger sample sizes. So I'm going to just pop back over the definition real quick and highlight something. So the sampling distribution of the sample mean is the probability distribution of all the values of the sample mean when all possible samples of size n are taken from a population. What does that mean? So that's exactly what they did here in this second table. They picked a sample size, which was 2, and then they found all possible samples of size 2, right? We had valves A through F. So one possible sample of size 2 could be valves A and B. Or we could have valves A and C, A and D, A and E, A and F. And then they keep going, right? They list every possible combination of these letters. And it turns out there are 15 of them. 15 possible samples of size 2. In these next columns, they recorded this first observation is the diameter of that first first valve, whatever letter it is. Second one is the second valve. And this last column here, X bar, is the notation for sample mean, which I'll write that out back on OneNote. I can't make any marks right here. But what they did is they literally calculated the mean of each sample, right? Sample mean is the mean of the sample. So like the mean of sample 1 is 0.1300. The mean of sample 2 is 0.1625, so on and so forth. Notice all of these are different, right? Which makes sense. All these valves had different sizes. So every sample is going to have its own sample mean, which is just fine. That's what we expect to happen. But also notice they're not too far off, right? They're all 0.1 and then something, something, something. So they're not like, this one's 0.1300. The other one's not 0.5892. That's far away. Just notice that these sample means, they're pretty close to each other. So this sampling distribution of the sample mean, basically, that's taking this last column of all these sample means and putting it into a distribution. And the distributions we've been talking about, I'm going to pop back over the notes. Distributions we've mainly been talking about is the normal distribution, which we will continue talking about that. And we'll talk more about that in the next section, actually. But remember, the mean is in the middle. And then depending on where a point lives on this horizontal axis, this refers to like how far we are from the mean. A point all the way over here is to the right of the mean, and it's farther than this point here, so on and so forth. The height here, the height of the curve, that usually refers to the frequency. How many observations we have, for that specific data point. So, basically, a sampling distribution of the sample mean is taking that list of sample means and creating a distribution with it. A graph with a mean in the middle, and then, the rest of the data points are down here, and depending on where they're located, tells you how far they are from the mean. So, popping real quick back over here. So we had all these sample means, right? And we put them into a distribution. Well, the middle of this distribution is going to be the mean of the sample means. I know that sounds a little crazy, but that's what it is. So the mean of the sample means. That's what would be in the middle. This is a distribution representing all possible sample means. And then right in the middle, that's the mean of your sample means. I know I keep saying mean a lot, but that's exactly what we call it. The mean of the sample mean. So just another quick example, because I found this picture online and I thought maybe this would be a little bit helpful. So, once again, we start with an entire population. Here's the mean of that population. And then they break everything up into samples, random samples. And in this case, they do samples of size 20. And they found the mean of, there could be more of these, but just for the sake of this picture, there's only 6 of them. So the sample mean for sample 1, sample mean for sample 2, so on and so forth. And then, basically, here in this last picture, they just took all those sample means and averaged them together. The average of the sample means, or in other words, the mean of the sample means, is 82.4, which notice is really close to the population mean, 82.5, which happens a lot, which is why we're looking at sample means, because they are very useful in estimating population parameters. Or in other words, the sample mean is useful in estimating the population mean. Okay, so I kind of just described this next part of the notes. Why calculate sample mean? Because even in this example, they gave us the mean because this is an example. But in the real world, you're not always going to have that population mean. So how do you figure it out? Using the sample mean. In fact, we're going to be using the sampling distribution and then finding the mean of the sample means. And then that's how we can figure out population mean. But again, it's really important that we have an unbiased sample, right? Because if we have a biased sample, then we will not be accurately estimating the population mean. It will be off. Scrolling down, last little bit for this section. A point estimator is a single valued estimate calculated from sample data, which is to serve as the best guess of an unknown population parameter. So this is literally what I was just discussing. We can't always figure out the population parameters, but we can figure out the sample statistics that will estimate those population parameters. And this little chart just shows us which estimator we like to use for the population parameter. So to estimate population mean, we like to use the sample mean. And here's the notation, X bar. X with a little bar on top, literally call it X bar. To estimate population standard deviation, we use the sample standard deviation, and we use an S for the sample standard deviation. Same thing with variance. Now, once again, we want everything to be unbiased. An estimator, which produces estimates centered around the true value, is said to be unbiased. And in fact, the sample mean is an unbiased estimator of the population mean. Now, we're not going to get completely into the nitty-gritty of that, but that is a fact that has been proven, and we will talk a little bit about that in section 9.3. So one last thing I want to mention is when you guys do the homework for this section, one of the questions is asking you, for example, what is the best estimator for population standard deviation? And they give you a list of all these symbols, and it'll be all these symbols: X bar, S, S squared, mu, sigma, and sigma squared. So they're going to be asking about the estimator for the population parameter. So if they want the estimator for the population standard deviation, your answer isn't sigma. What's the best estimator for this parameter? Sample standard deviation, S. So just be very careful when you read those questions. I'm saying this because I've taught this before, and that always ends up being a question. People get kind of confused. But again, they're asking for the estimator, not the actual symbol for the population parameter. All right. So I will see you guys again in section 9.3.